Good morning, and thank you for joining Spec Innovation's webinar, Dissecting SysML 2.0 with Lilleigh Stevie. My name is Elizabeth Steiner, and I will be the moderator for today's webinar. First, let's go over some quick housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the question and answer part of the webinar. You can also interact with us on LinkedIn through the InnoSlate user group. The webinar is being recorded, and we will make it available to you after the live presentation, so be sure to keep an eye out for it in your inbox. Now I would like to introduce you to our presenter, Lilleigh Stevie. Lilleigh Stevie is a systems engineer at Spec Innovations. She's seeking her master's in systems engineering at George Mason University. As a systems engineer at Spec Innovations, Lilleigh has worked on contracts with MDA and NASA. She was one of our key engineers who worked on the digital engineering of a lunar rover project. Lilleigh helps develop the requirements for InnoSlate and Sapatra. She also has played a vital role in the research of SysML 2.0 for InnoSlate. And now I'll hand over the controls to Lilleigh and we will get started.
Hi everyone. So today we're going to go through the background of SysML V2 as well as the purpose and objectives for it. Then we're going to cover what is KerML and what is SysML V2. And then we're going to dive into the actual language and concepts of SysML V2. Then discuss where this takes us and some of the shortfalls of V2. So SysML V1 was adopted in 2006 and has been used across the MBSE industry. From its use, everyone's learned both strengths and weaknesses, and those weaknesses have prompted the creation of V2. It also outgrew UML when building SysML and UML became difficult and SysML began to become its own language. The System Engineering Domain Special Interest Group is an OMG working group. They are the ones that developed requirements for the next generation of SysML, as well as the OMG RFP for SysML V2 language that was released in December of 2017. And the OMG RFP for standardized SysML V2 API and services that was released in June of 2018. These RFPs led to the establishment of the SysML V2 submission team, or SST, which consists of over 200 people from over 80 organizations. So SysML V2 is a general purpose modeling language for modeling systems that is intended to facilitate a model-based system engineering approach to engineer systems. Their objective and creation of SysML V2 was to improve the precision and expressiveness of the language, the consistency across the language concepts, the usability for model developers and model consumers, the interoperability between systems, modeling tools, and other model-based engineering tools, as well as to improve the extensibility to support modeling of domain-specific concepts. So what is KerML? KerML stands for the kernel modeling language. It was created by the SysML V2 submission team to be a modeling language to create modeling languages. And it consists of 3 meta model layers, which you can see on the right in the diagram picture. So the base layer is called the root layer. It is the most general syntactic constructs, which includes the elements and relationships between them, annotations of elements, and the membership of elements in a namespace. The next layer up, with a little bit more specific, is the core layer, and it consists of the most general constructs that have semantics based on classification, which includes the type, feature, and classifiers. A little bit more specific is the kernel layer, which provides commonly needed modeling capabilities such as classes, data types, structure, associations, connectors, behaviors, interactions, and all the other ones. It is the foundation for SysML V2, which we'll talk about right here. So that 4th layer is the systems layer in the meta model. You can see at the top of the picture on the right, the systems layer specializes the KerML to include domain-specific concepts. Some of the meta classes are either reused from KerML or extend the KerML meta classes. So KerML actually establishes a pattern of definition and usage, which gives it a usage-oriented modeling technique. And we'll discuss the difference between the definition and usage and how they're used. SysML V2 also provides a textual notation and a graphical notation, which are supposed to be equal. So if you have a textual notation, you can translate to the graphical and vice versa. So the graphical notation, there's supposed to be diagram types that will be defined to facilitate the transition from SysML V1 to V2. I've seen a couple of them. I don't know how well they're defined yet. As well as they're going to not constrain what element types can be on a particular diagram, so long as it conforms to the meta model. So it gives a lot more freedom to diagrams. As well as SysML V2, they also added the extendability concepts to build those domain-specific extensions. So now we are going to dive right into SysML V2. So I'm going to start with some basic concepts and build on them. And I'm also not going to cover everything because there is a lot to V2. So I'm going to cover the basic high-level concepts. So firstly, there are some pilot implementations that were developed to pilot the language and test it as they were developing it. I used the Jupyter Lab pilot implementation to create the following examples. It uses a SysML V2 language kernel that SST keeps up to date, as well as a tool called GraphViz that just allows it to display graphical views of the text. If you want more information on the pilot implementations, those can be found at the SysML V2 release GitHub, as well as a bunch of other information about the V2. So the first concept is a package. So package is essentially the same as it was in V1. It is a container for elements to organize a model. So I'm going to use these orange squares to highlight the different sections of text that I'm going to be talking about, as well as different sections of the diagrams. So up at the top, you should see an orange rectangle containing the package Lunar Rover architecture. So this package Lunar Rover architecture actually contains all of those parts that are within it, and they're contained by those curly brackets. So for parts are units of structure. So here we have the part Lunar Rover that we're modeling, and then it's broken down into the part battery, part body, part motor, wheel, brake, communicator, camera, and sensors. So a part may also have attributes, ports, and it may perform actions, and it may exhibit states. I will talk about the attributes and the ports today. You can look more into the other ones. So for the GraphViz, the percentage viz is kind of how it starts, and is the command that it allows you to visualize the textual language as whatever view you want. For instance, this view is a tree view, which gives you that decomposition. So you can see the Lunar Rover is decomposed by all of its subparts. So next we're going to add a few more aspects. So the first one is import. Import works the same as it did in V1, where you can import libraries and you can import packages for use and reuse. So when you import a package, you can access the definitions and the usages that are contained within it. So that's where they get the reuse. So you can see in the upper left-hand corner, it says import scalar values that has : : star, and that imports the entire library of scalar values. So in this slide, we're going to talk about the definition and the usage, which allows that reuse in different contexts. So you can define one thing and use it in multiple contexts. This is employed throughout the entire SysML V2 language, and it applies to all element types. So a definition elements classify or define a type of a certain element before its use, and a definition may have nested owned usage elements called features. So the orange rectangle highlights the part def sensor, which has a feature attribute called min voltage of type real. And this is used further down in the part decomposition. So a usage element are usages of a definition element in a certain context. So each usage element must be defined by at least one definition element. If not, it is then implicitly defined by the most general definition of the same type from the SysML V2 library. So for instance, part body, I did not define a definition for. So the part def is part. So they just use that same, the most vague. A usage element may have nested usage elements as features and may have a multiplicity. So multiplicity is denoted by the square brackets after the usage name and can be a range or a single number. So this can be seen with part active remote sensor. It has that bracket 2. So there will be two active remote sensors. And in that line, active remote sensor : sensor is a defined by relationship, which is represented with the colon. So attribute definitions, which are currently highlighted with the orange square on the upper left, define a set of values that could be data values, qualitative values, quantitative values, or any data structures of such values. Attribute usages are usually a feature of a part, which you can see in the next rectangle below it. And in order to define these unit types, that's where that import is really key. So the import scalar values gives you the integers, real, imaginary, etc. So attribute def resolution has another attribute called resolution integer. And then it is used in part camera. So camera has an attribute called cam resolution, which is of type resolution. So then it can be seen in the diagram on the bottom right that active remote sensor, temperature sensor, and pressure sensor are defined by the part definition sensor, which they've denoted with arrows with 2 dots. So definition and usage elements can be specialized using subclassification and specialization. So on this slide, we're going to talk about subclassification that specializes a definition. So its subclassified definition element inherits the features of the more general definition element, and other features can be added. And a subclassified definition can have one or more generalizations. So in this case, we have part def active remote sensor, which specializes a sensor. And we have a part def passive remote sensor, which also specializes sensor. So there are 2 notations that you can use: a shorthand, which is the colon greater than, or you can type out specializes. But the definition part def sensor also contains an attribute. So active remote sensor and passive remote sensor inherit that attribute. So then this is how they show it in the diagrams currently. So you still have the defined by with the part def for active remote sensor and passive remote sensor and their usages. But the single arrow with no dots is a subclassification to part def sensor. So next is the subsetting of specialization, which applies to usages. So subsetting specializes a usage element and is a kind of generalization between features. So for this example, we have part mobility, which is defined by mobility subsystem. And then there's part battery, part body, as well as part motor, which is subsets mobility, part wheel that subsets mobility, and part brake that subsets mobility. So motor, wheel, and brake are more specific instances of the mobility part. So another kind of subsetting is redefines, which applies to usages and definitions. So a specialized definition can redefine a feature that would be inherited by the specialized definition. So in this instance, we have the part def sensor has attribute min voltage of type real. That leaves it general. So if we specialize part def active remote and part def passive remote sensor that specialize the sensor, we can redefine the attribute min voltage. So for active remote sensor, the attribute is redefined so that min voltage is equal to 5. And for part def passive remote sensor, the attribute is redefined to be min voltage is equal to 3.3. So there are two notations here as well. So redefines is, you can type out redefines, or you can use colon greater than greater than. So this is another diagram that shows both types of specialization, subsetting, and subclassification, as well as redefines. So on the left, it shows the subsetting, and on the right, you see the redefines with the subclassification. So next, we're going to change it up a little bit and go to kind of the equivalent of the internal block diagrams and how that they've changed them in V2. So first, we're going to talk about items. So items are classes of things that exist in space and time, but are not considered parts of the system. They may be things that are stored in and or flow between parts of a system. So it's important to note that all parts can be treated as items, but all items are not parts. So in this instance, in the upper left, I have defined an item energy. So we're going to use that item and for our ports. So ports define a connection point for interactions, and the port usage may be connected to one or more other ports. A port can have features that specify what can be exchanged and in what direction. So ports are compatible if the directed features match with the inverse directions, and each port has an implicit conjugate port definition that reverses the input and output features, as well as ports can be nested. So what's currently highlighted is the port def power out port, which has an out item power supply typed by energy. So this is then used within our lunar rover decomposition to show the interconnections between the parts. So part mobility system has a port power in, and you can see that little squiggle for not power out port, which gives it the conjugate port. So the power in will be the conjugate of the power out port. Part battery has port power out, which uses the power out port definition. And you can see all the other ports as well going down. So a new concept that they, well, not quite new, but new defined explicitly is the interface element that are used for a specification and reuse of compatible connections between parts. So an interface definition is a connection definition whose ends are only port definitions. So the interface usage connects to compatible ports. So currently highlighted is the interface definition power interface, which gives one end is a power out and one end is a power in port. So then this is used with interface, power interface connect, and then it'll have a power out, which is connected to a battery power out, connects to a power in, which is specialized by that communicator power in. You can see here that the battery dot power out is a dot notation to access that port through the specific entity battery. That's just a good way to access those things within a decomposition, and that's used throughout the language as well. Okay, so the next concept on this slide is connection. So connections, there are two types. Connections are relationships and a kind of part that classifies connections between related things. And for the internal block diagram concept and be able to show the interconnections, you have to connect each one individually. So you have to connect, like here it's connected body to battery, body to mobility subsystem, body to communicator, body to camera. You can also connect the ports. So there's a connect battery dot power out to mobility subsystem dot motor. And you can kind of see that with the diagram above. The little squares are the ports and all the lines are the interconnections. So one of the things with the pilot implementations is that you can't alter the diagrams that it creates. So it just generates this and it'll look terrible because there's no layout feature at all. Hopefully with tooling, that'll be fixed in the future. So there are two other types of connections that are called binding and flow connections. Binding connections are binary and assert an equivalence of the connected features, and flow connections actually transfer some payload between the ends of the connections. All right, so now we're going to shift gears to the behavior of our example with the actions. So actions are defined as occurrences over time that can coordinate with other actions and generate effects on items and parts involved. Actions can be decomposed and have parameters. The order of actions is specified by succession, which is denoted by a then in the textual notation you can see on the left. Succession can be conditional with guards, and an action can be performed by a part or another action. The same control nodes from V1 are present in V2. So there are merge nodes, decision nodes, fork nodes, and join nodes. Additional structured control actions have been added, and that includes an if action, a for loop action, and a while loop action. So those are going to be pretty a different aspect to the action diagrams that didn't exist in V1. So this example I created was kind of basic and tried to show some of what the action diagrams will look like as textual notation. So with an action, you have to do a first start, which gives you a start node. And every action after that will be followed by a then. So then action power on, then merge continue, then fork, and then fork you can indent, and it contains then action communicate with earth, then action traverse surface, then action collect data, then action monitor charge, and you can output a charge, and that charge can be used. So after the join node has joined back together, you can have this one has a then decide. So if the monitor charge dot charge is less than 30, then it'll continue. If the monitor charge dot charge is greater than 30, then it'll return to charge. And then you have to define an action return charge, and the then done gives you that end node. So they're not as straight, it's not as easy to model an action diagram through the textual notation. And it was kind of a struggle to get it to this point. So I'm kind of interested to see how it'll be handled in the future. So next is the concept of constraint and requirement. So a constraint is a reusable parameterized Boolean expression. I only used one of these in the example and didn't really define it because a requirement is a child of constraint. So requirements are typed by constraints now. So it specifies, the requirements are supposed to specify a stakeholder imposed constraint that must be satisfied for a design to be a valid solution. So a requirement can have a textual statement, can require constraints, and may have additional and assumed constraints, as well as be parameterized and can specify the subject. So this is, for this example, the doc entity, which is part of a comment annotation one, gives the full sentence of what the requirement states. So the lunar rover shall have a mass of less than 12,000 kilograms. So that is a kind of appended as a like annotation to the entity. And below that, we have an attribute called actual mass that's typed by a mass value, as well as an attribute called max mass, which is typed by a mass as well as by a mass value. So then we require the constraint be that the actual mass be less than the max mass. So if you can see at the top of the screen, there's a part lunar rover that has attribute mass is equal to 987 kilograms. So that is what's treated as the actual mass. So when we do a usage of the requirement, we can give the requirement a number as well as a name and define it to that requirement definition. And then each of the requirement definition's attributes can be redefined to bind the requirement definition parameters to a specific value. So the attribute actual mass is redefined to equal the lunar mass dot mass, so that 987 value. And then the attribute max mass is redefined to be 12,000 kilograms. So then that requirement is satisfied because the actual mass is less than the maximum mass. So next is a new concept for V2 that is explicit, which is the concept of variability. So variability can be represented in SysML V2 with variations and variance. So a variation can be applied to any definition or usage, and it can be nested as well. The variation identifies a variation point, and then the variants are defined at that point. This allows a choice to be made to select a specific variant for the system. So for this example, I used part sensor subsystem, which contains a variation of part proximity sensor. And I defined two variant parts to be LiDAR and radar. So further down, you have part lunar rover 11. So that's the specific lunar rover and is a subset or specialization of the lunar rover itself. So then we can redefine the part LiDAR to be the sensor subsystem dot proximity sensor. So then in the diagram, you can see that under sensor subsystem, it has a variation part called proximity sensor that contains two variants, LiDAR and radar. So I'm going to give an overview of some of the other elements that I didn't go into depth on. So they've also defined a dependency, which is a kind of relationship between any number of source and target elements, so that any change to a target element may result in a change to a source element, as well as the overarching class called occurrence. Occurrence is a class of elements that have an extent in time and may have an spatial extent as well. And this honestly contains what's below it. So the time slice, the snapshot, it contains state, it contains actions. It is one of like the big classes in SysML V2. So time slice and snapshot are also new concepts to V2. So time slice represents a period or phase of a lifetime for an occurrence over some period of time. So it could be from time A to time B, and that's what the system looks like. Then for a snapshot, it represents an occurrence at a specific point in time. So what does the system look at time A? Connected to those is an individual, which is an occurrence of any kind that can be restricted to model a single individual and how it changes over a lifetime. So you can define an individual and then look at the snapshot or the time slice of that individual in the given system. For states are types of actions, as well as the transitions that connect states are also types of actions, and it can be exhibited by a part. So not much has changed surrounding states in V2 versus V1, except the definition that a state and transitions are subclasses of action. Then we also have a calculation, which is a reusable parameterized expression that returns a result. This is similar to like the parametric diagram in SysML V1. And then we have cases. So there's an analysis case, verification case, use case. I also didn't put on here that there is like a trade-off case and an overarching case class as well that contains the four of them. So an analysis case defines the computation of an analysis of some subject in order to meet an objective and output a result. A verification case defines a process for verifying whether a subject satisfies one or more requirements. And a use case specifies a sequence of interactions between the subject and various actors, modeled as part usages, and the interactions are modeled as messages. So use cases are pretty much the same as they were in V1. And then there's a new concept called a viewpoint. So a viewpoint frames the concerns of one or more stakeholders regarding info about a modeled system or a domain of interest. So you can take in a stakeholder input and create that viewpoint to show them what they want to see. So I think that's kind of it's a new and a good concept that they added. So one of the key things that they were supposed to create with the second RFP was API and services. So the API that they've defined is used to navigate and query the model, to create and update model elements, to establish version control to support configuration management, and to manage relationships with external data. So the specification includes the platform independent model, the PIM, which is the logical API model and provides a specification of services independent of platform and technology. And then it also defines two platform-specific models, or the PSM. So the bindings of the PIM to a particular platform and technology. In this case, they've used the REST HTTP and the OSLC 3.0. I know that the REST HTTP runs off of querying and returning JSON, and it's kind of a hope that there will be some kind of export in JSON as well. Not really sure about the OSLC. I know it's been up and coming in the industry, and that's why they're pushing it with this. And hopefully the API will work well in interchanging and exchanging information between tools. So where does this take us? So the SST is finalizing the specification documents and artifacts for this month's OMG meeting to submit early, because their submission is in November of this year. So they want OMG to start taking a look and start the adoption and finalization process in December and January. Supposedly, there's going to be a beta specification to be released at the beginning of next year of the SysML V2 language, and the finalization process will take most likely until 2024. And there's a hope that the 1.0 specification of SysML V2 is to be released early to mid 2024. So some of the shortfalls that I want to discuss that I found while doing all this research and creating this presentation was that SysML V2 with the textual notation makes it very difficult to visualize what you're modeling. So you can have this mental image of what you want to show and what you want it to include, but trying to take that mental image and convert it into a textual based notation was not easy. I just wanted to be able to drag the entities and put them where I want to and then define them that way. So I'm hoping with the implementations in tools by tool vendors that you get that you can either create it with the graphical notation or you can create it with a textual notation. I know that some people might find the textual notation easier. I do not. I like the graphical notation and I like being able to see what I'm creating. Especially with like that action diagram, trying to define actions in a textual way was not easy. It took me a while. Another thing is the learning curve. So now that there's a textual notation and a graphical notation, we're going to be expected to learn one of them or both of them to be able to use SysML V2. And that's not going to be easy, and it's not going to be done in a short amount of time. So the specification of SysML V2 is over 700 pages long, and I read a good portion of them, and some of them are some concepts are easy to understand, some of them are not. And I've been doing the research since January, and I still feel like I barely understand like 20% of the language. It's still complex. It's usable. It's much more usable. It's much more easy to use than V1. But there is a decent learning curve on understanding the concepts and understanding how to use and define them in the textual notation, as well as the graphical notation. And with that, since it is a complete overhaul of a brand new language, it's going to take a long time to implement in tools, especially with the specification not going to be finalized until 2024. And these tool vendors having to create entirely new tools to handle both the textual notation and the graphical notation at the same time. So we'll see how long it will take and how fast these tool vendors will have V2 modeling capabilities released. So as a solution, in the meantime, there exists the LML, or the Lifecycle Modeling Language. So the Lifecycle Modeling Language was developed to support the full lifecycle and help solve many of the problems of SysML V1 as well. So LML has a smaller set of entities with 12 primary classes and 8 subclasses that are differentiated by attributes. Almost every class is related to every other class and may have multiple relationships between them. There are even attributes on relationships. All of these help to ensure that it is quick to learn and easy to understand, but can also be used to model complex systems. So if the classes and relationships don't fit what you need, all classes are extendable, as well as relationships can be added and attributes can be added in both classes and relationships to fit what you need. So LML was then used as a language for the tool Innoslate. Innoslate is a cloud-based full lifecycle software to support model-based system engineering, requirements management, verification, validation, and project management. So if you want to learn more about the lifecycle modeling language, you can go to lifecyclemodeling.org, or if you want to learn more about Innoslate, you can go to innoslate.com. So these are all of my references that I could find. There's not much on V2 outside of some key webinars and podcasts as well, but the huge resource is the one at the bottom called the SysML V2 Release GitHub, and the one above it, which is the MBSE 4U SysML V2 Jupyter Notebook. That Jupyter Notebook provides examples of how the textual notation is used, as well as explains some of the concepts. And then the GitHub has literally everything. So check it out if you want to learn a little bit more in depth about SysML V2. Thank you.
Thank you, Lily. We've already received several questions. If you haven't done so, please use the panel on the right to ask your questions. We'll go ahead and get started right now. Lily, your first question is, does SysML allow the user to generate the model visually, or is the SysML 2.0 code required?
So currently it's up to tool vendors. In the current pilot implementations, you have to do it textual notation first, and then it'll generate graphical notation, but they want tool vendors to decide to either do textual notation only, graphical notation only, or a combination of both, to make it so you can interchange, you can type out something textual and convert it to a graphical, you can did a graphical and then converted to a textual. They want them to be interchangeable and equivalent.
Thank you, Lily. Your next question, does the action in SysML 2.0 replace the activity in SysML 1.0?
Yeah, it does. They just took the term activity and simplified it down to an action because they didn't want to reuse many of the terms that were used in SysML V1 to kind of separate it from V1. So that's why you see a lot of different terminology. And an action is just a better word for it anyways, because that's what it is.
Thank you. Does verification case replace test case?
In a way, I would say yes. But they also have that analysis case. So you can define a vague case. It's up to the user if you want to do that verification case to establish a test case, or if you want to do an analysis case as a test case, or there's even like a trade-off case, or you can create your own with the case, the high-level case, if you wanted to define a more specific use case, if that makes sense.
Thank you. Your next question is, given the shortfalls identified, what is the value proposition for a program manager or chief systems engineer to transition their engineering efforts away from SysML 1.0 to SysML 2.0? Lily, do you need me to repeat that?
Yeah, if you could.
Yeah, absolutely. So given the shortfalls identified, what is the value proposition for a program manager or a chief systems engineer to transition their engineering efforts away from SysML 1 to SysML 2?
So I think they hope with V2 is that it'll be easier to define concepts, and it'll be more clear when modeling, because V1, there is something like you can have some ambiguity with V1 and some complexity with V1, and they're trying to get away from that with V2 to make it that precise and concise and expressive language, rather than like V1 where you're not really sure what you're looking at. Where with V2 they want to make it so your stakeholders can actually view it and understand it a little bit better. Hope that answers the question.
I think that answered the question. And please let us know in your questions. You can let us know if that answered your question or not, or if you have additional questions. How compatible is SysML 1 and SysML 2? Can I migrate my SysML 1 models to SysML 2? Can I save my SysML models in SysML 1?
I believe that is the hope with it. This week they released the full document documenting the migration from V1 to V2 and every single attribute and how in V1 and how it maps to V2. So there will be that interchange between the versions. I know that with the transition, most of it maps. There might be some loss of information that doesn't translate. But you should be able to have a model in V1 and be able to transition it to V2 in the migration forward.
Wonderful, thank you. On the activity diagram, was it intentional that the fork did not have a single input and multiple outputs flows?
Oh, wait. Let me go back to that. Okay, what What was the question about?
Oh, would you like me to repeat the question?
Yeah, if you could.
Absolutely. Hold on. I think I lost it here for a second. On the activity diagram, was it intentional that the fork did not have a single input and multiple outputs flows?
I wouldn't say it was intentional. It might have just been difficult to add to this notation. I would think it was one of those things that I was still trying to figure out how to model, because the action diagram was not, it looked straightforward, but trying to add those like item flows was a little bit more complex. Because I even tried to use like the if or for loop actions and could not get them to work.
Thank you. Your next question is, can organizations have spent a lot of time and money educating their workforces in SysML 1? SysML 2 seems different than SysML 1. Are organizations going to have to retrain their organization's SysML modelers?
I would say yes. Is they did keep some of the original SysML V1 concepts, and people that know SysML V1 shouldn't have that hard of a time transitioning to V2, but there definitely are a lot of new concepts and a lot of different ways of modeling that do require training.
Thank you, Lily. Our next question is, SysML 1 has 4 pillars and 9 diagrams. The SysML RFP listed an additional 4 pillars for a total of 8. What new diagrams are available with SysML 2?
Some of the new diagram types that they've talked about or sort of defined in the specification is mostly renaming. So like the interconnection, there's an interconnection view, which is essentially the IBD. There are different decompositions, so which they've termed as trees. So there's a part tree, attribute trees, action trees. I can't remember the rest off the top of my head, but they're different names for some of the same diagrams that exist in V1.
Thank you, Lily. Next question is, SysML 1.0 is based on UML. SysML appears to be significantly different. Does this represent a divorce between SysML and UML?
Yes, they wanted to completely separate themselves from UML. And they did that with the kernel modeling language. And this was mostly because SysML just got too large to sit on top of UML. SysML V1 had over like 200 entities. And a lot of them didn't get used, and a lot of them were from UML. So they just took out the concepts from V1 that were usable, that people used, that people liked, and implemented those in V2 and completely separated SysML V2 from UML.
Thank you. For last question, what programming languages do you need to know to work with SysML 2?
Hopefully none. I know that a lot of system engineers have coding backgrounds and a lot of them do not. And the language itself is not like any other programming language. So knowing a programming language won't help you. Even like one of our programmers was like, this is not programming. This is something entirely different. And it is. it's its own textual notation. It's not code, and it's not going to be useful if you try to think of it that way. Because everything in the textual notation will have an equivalent graphical notation, or almost everything.
Thank you, Lily. That's all we have time for questions today. If you have any other questions, please feel free to reach out to us after the webinar. We'd like to thank you again for joining us and for your participation today. We hope you learned a lot about SysML 2.0. As a reminder, we will be following up with you very soon to send you a link to the recording and the presentation slide deck. Our next webinar is on October 19th at 11 o'clock a.m. Eastern. We'll be answering the question, what comes after MBSE? We also encourage you to visit our website, check out our books and our blogs, as well as connect with us on social media. That concludes today's presentation. Thank you again for your attendance, and we hope to see you again at our next webinar in October. Please enjoy the rest of your day.